In this video, we'll talk about polar coordinates, which give us a new way to analyze points and graphs on the plane, which can make it easier to do calculus on these sorts of curves. The point of polar coordinates is that it models certain graphs and certain curves really nicely, makes it really easy to do calculations with them. It gives a new way to analyze how we write a point in the plane, which will make it easier to analyze certain types of functions. So a new set of coordinates we have defined as r and theta, as opposed to the x and y, which are normally called the Cartesian set of coordinates. We define these points r and theta in polar coordinates as follows. R is distance from the point that I care about to the origin, or the 0, 0, the intersection of the axes. And theta is the angle that this line makes with the positive x-axis, where I'm counting angles in a counterclockwise direction. So picture's probably easier. Let's draw a picture. If I have the point up here, which is normally defined by xy coordinates, I want to define it by r and theta. Well, how do I get r and theta for this point? Well, r is the distance from that point to the origin. So I take the origin here and I draw the line out to this point. This length here is r. And theta is the angle that this makes with the positive x-axis when I count counterclockwise. So this here is my angle theta. So this point would be given by r theta, where r is that length and theta is that angle. If I took another point, say a point that's out here, wanted to find that r and theta, well, again, r is the length out to the point, and theta is the angle with the positive x-axis. But for that one, I have to start here and go all the way around here, and that angle gives me theta for this point, r theta out here. So r is always distance to the origin from the point, and theta is the angle of rotation to get to that point from the positive x-axis. If I wanted to point all the way down here, here would be r, and theta has to go all the way around to get to this point. This way does not give me theta, because that's not the counterclockwise. I have to go all the way around the other way to get to what theta should be for that point down there. So there's a couple of examples. We want to find the polar coordinates of the point xy is 3, 3, and then find the rectangular coordinates, or the Cartesian coordinates, from the polar coordinate point for pi over 3. So for 3, 3, let's plot that point and see what we get. So the point 3, 3 is up here somewhere. I want to find what this is in polar coordinates. How do I do that? Well, let's draw in a triangle here. And now I can figure things out. This should be my r, and this should be my theta. And what do I know? I know this side is 3, and this side is 3. That gives me all I need to figure out these coordinates. So r should be square root of 3 squared plus 3 squared, which is square root of 18, or 3 square roots of 2. And based on my triangle here, I know that the tangent should be 3 over 3, or 1, so theta should be the inverse tangent of 3 over 3, which we know is pi over 4. Inverse tangent of 1 is pi over 4. So in polar coordinates, this point is written 3 square root of 2 and pi over 4. We can go the other way as well. So if I have the point 4 and pi over 3, means I need an angle here of pi over 3 and a radius of 4 to get out to my point, which in polar coordinates is 4 pi over 3. To find the rectangular coordinates, I need to figure out the x and y here, which I can do by, again, finishing up this triangle. This will be y, and this will be x. I have the hypotenuse and an angle. I can then figure out what these sides are. So from this triangle, we can see that sine of pi over 3, opposite over hypotenuse, should be y over 4, telling me that y should be 4 sine of pi over 3, which is 2 square root of 3, because sine of pi over 3 is root 3 over 2. And similarly, cosine of pi over 3 should be x over 4, so that x is 4 cosine of pi over 3, which is 2. So in rectangular coordinates, this point is 2 square root of 3. So that gives you an idea of what polar coordinates are and how they change how we write points in the plane, but haven't really said why they're useful yet. And that will come when we start talking about what kind of curves polar functions are great at modeling, and then we'll see that they're really hard to write in rectangular coordinates. So if I can write them in polar coordinates instead, my life will be a lot easier for trying to do calculus on these sorts of functions.